Assalamu alaikum everyone. This is Inshirah. This is your topic 7, and in this video you're going to learn about chemical reactions. So, the topics that you're going to come across are rate of reactions, how to control rate of reactions, and what happens when you plot graphs. The first thing that you need to know is the difference between physical and chemical change. A physical change does not result in the formation of a new substance. It simply alters the state of the substance involved. An example is when you melt ice, it turns into a liquid water. Now you can see that both contains water, H2O. Both ice and liquid contains the molecule H2O. What actually changed is the state. We know that there are 3 states of matter: solid, liquid, and gas. So a physical change is not forming a new substance. It is simply changing the state from solid to a liquid. Similarly, if you boil liquid, you will get steam in the form of H2O. And this is also a change of state from liquid to gas. And you can also convert it from gas to liquid and from a liquid to back to its solid state. However, in a chemical change, the formation of a new substance is formed. In physical change, there was no formation of a new substance. In a chemical change, any reaction will form a new substance. An example is the decaying of organic matters or ripening of apples. Once an apple ripes, you cannot convert it back to its original form. And we say that there is a chemical reaction occurring inside. So, in a physical change, it is possible to reverse the change, and the change can be temporary. An example is when water from melted ice can be frozen back to its former ice state. So now you know what a physical change is. But in chemical reactions, a chemical change occurs, and that is entirely permanent. And this is universal for all chemical reactions. An example is the burning of solid fuels, such as coal, can be said to be involved in a chemical reaction taking place. Another example is rusting of iron. Rusting of iron occurs in the presence of water and oxygen. An orangey red powder forms on the surface of the iron rod. And that is a chemical reaction. So now you know what is the difference between a physical change and a chemical change. Now, how do you know whether a chemical reaction has taken place? These following observations will allow you to recognize that a chemical reaction is occurring. The first thing that you need to know is the formation of solids. If there is a chemical reaction, there will be a formation of solid in the form of precipitate. If there is a chemical reaction occurring, there will also be a formation of new order. Another method is there will be just a change in color, formation of gas, bubbling or fizzing, or the release or absorption of heat, which is change in temperature, also known as endothermic or exothermic reaction. Now you need to keep in mind that all of these reactions may occur together in a chemical reaction, or it may also be individually observed. If you see a chemical reaction occurring, there must be no reaction, just the formation of a new order. Sometimes you will see that there is no reaction except a change in color. Sometimes you will see very bubbling and fizzing formation. And sometimes there will be nothing at all, just a temperature rise and a temperature drop. So all of these five observations can either be seen directly or it will occur individually. And by that, you will recognize that a chemical reaction has been taken place. Next, you need to know about collision theory in order to know what actually is happening inside. This theory states that for a chemical reaction to take place, two things must happen. The reactant particles need to collide with one another, and the particles must collide with enough energy. We know that all matter is made up of particles. So, the two things that you need to understand is the reactant particles must collide, and they must collide with enough energy. As you can see here, these two particles are colliding with one another. If they collide with enough energy, they will allow the bonds to break and form a new substance. If they collide with enough energy, we call that the collision is successful and the reaction will take place. So, whenever you know about a reaction or whenever you see a reaction occurring, you must know that in order for a reaction to take place, the particles inside must collide with one another and with enough energy. If they do not break with enough energy, the reaction will not occur. If they do not collide with enough energy, reaction will not occur. They will just bounce off from one another. And this is known as unsuccessful collision. So, we know that our matter is made of particles, and the reactant particles must collide with one another and they must collide with enough energy so that the bonds are broken and new substances are formed. And this collision is known as a successful collision, which means a reaction will take place. However, if they do collide but not with enough energy, no reaction will occur. As you can see, two particles are colliding but they do not have enough energy, so they will just bounce off each other. And so no reaction will take place because the collision is unsuccessful. If the particles have enough energy but they're not colliding with one another, then also the reaction will not occur. So now you know the two reasons for a reaction to take place. The first is particles must collide with one another, and the second is they must collide with sufficient energy. And then we say that a successful collision has taken place, and so the reaction will proceed. Now, what are the factors for a successful collision to take place? There are four things that you need to keep in mind. The first is activation energy, also known as EA. This is just an abbreviation for writing activation energy. The second is frequency of collision between particles. The third is kinetic energy of the particles. And the last is the number of particles per unit volume. These four factors affect a successful collision. Activation energy, also known as EA, is the minimum amount of energy required for a chemical reaction to take place. According to collision, we learned particles have to hit each other, but the hitting should be hard enough to overcome this push for reaction to take place. So, whenever there is a collision of particles, the collision should be greater than or equal to activation energy in order for a reaction to take place. Here is just an example of illustrating activation energy. Let's say there is a very large hill that you need to pass using your car to go over to your home. Now, when this car moves up the hill, you need a force. And that force comes from engines, right? You need to go against the gravity. So, this force to overcome the push is known as the activation energy. And that is why we say that when collision take place, they should collide with enough energy that should be equal to or greater than activation energy. Equal to or greater than activation energy. Only then the reaction will take place. Next, frequency of collision between particles. The more collisions there are between reactant particles, the greater is the chance that they will collide with enough energy to undergo a reaction. We know that particles collide with each other constantly. But if the frequency of collision between reactant particles increases, there is a greater chance that they will collide with each other with sufficient energy that is equal to or greater than activation energy, and so there is a higher chance for a reaction to take place. Because if particles collide with each other, we know that the chances of a successful collision will increase. Next is the kinetic energy of particles. Kinetic energy is known as the motion that particles have. If there is a high energy, it means that it will increase the number of successful collision and thus will increase the rate of reaction. What is kinetic energy? Kinetic energy is the motion of the particles. If particles have high energy, this will increase the number of successful collision because we know that for a reaction to occur, the first thing is particles must collide with each other, and the second thing is that they need to have energy that is greater than or equal to activation energy. Only then there will be a successful collision and a reaction will take place. So, if particles have high energy, this will increase the number of successful collision and so will increase the rate of reaction. The next is the number of particles per unit volume. Let's say you have two liquid reactants. One has a very low number of particles and the other has a very high number of particles. The more particles there is present in a specific volume, the higher there is the chance of successful collision between particles. Both have equal volume, let's say 100 centimeter cube. That one has very low particles, that means low concentration, and the other has very high particles. In other words, we can also say high concentration. This means that these high concentration will have more particles present in a specific volume, and so there is higher chance for particles to collide with each other with enough energy greater than or equal to activation energy, and so there is the higher chance of successful collision between particles and the reaction will proceed. However, if the particles present in a specific volume is low, the chances of the particles to collide with each other will also decrease. And so, there is a lower chance of successful collision between particles and a lower chance for a reaction to take place. Now we can start with the rate of reaction. What is the rate of reaction? Rate of the reaction is the speed of the reaction. It refers to how quickly the reactants are consumed and the products are formed in a chemical reaction. It measures how fast or slow a reaction occurs. Now, there are many chemical reactions that are so fast that explosions take place. And sometimes the reaction is so slow that it takes weeks to undergo. And most of the reactions undergo in a medium rate. Now, scientists or chemists are looking for ways to control a rate of reaction. And they have found a total of 5 ways in which you can alter and control the rate of a chemical reaction. There are 5 methods, which includes changing the concentration of solutions. If you increase the concentration, there will be more particles present, and so there is a higher chance for successful collision to take place, and so the reaction will be faster. The next is changing the pressure of gas. If you increase the pressure, let's say you have a tube containing oxygen gas. If you increase the pressure by pressing the plunger, the pressure of the gas will increase and we are going to squeeze all the particles, and so the particles will be in contact, which means they will be colliding with each other and there is an increase of successful collision. So, increasing the pressure will increase the rate of reaction. The next is changing the surface area of solid. Let's say that you have a solid and on the other hand you have these powdered solid, both are the same. If you add powdered metal in a reaction, let's say, between acid and metal, if you add powdered metal in an acid, the reaction will be very fast and vigorous. However, if you put a solid metal into an acid, the surface are only coming into contact with the acid. And so, this reaction will be very slower than a powdery substance. So increasing the surface area will increase the rate of reaction. The next is changing the temperature. Increasing the temperature increases the kinetic energy of the particles and so there will be more successful collision.
And lastly, you have the addition or removal of catalysts, including enzymes. Catalysts are substances that increases the rate of reaction without being involved. They themselves do not react. If you were to add a catalyst into a mixture of reactants, the catalyst simply speeds up the chemical reaction to form a faster rate of products. But catalyst remains unchanged from the beginning to the end of the reaction. Now, in order to understand all of these 5 reasons by which you can control and alter the rate of chemical reaction, you must understand the concept of collision theory and you must know how of these changes are taking place by terms of collision theory. So first we are going to look at the concentration of reactants in a solution. Earlier, we saw that increasing the concentration of solutions increases the rate of reaction. Let's say you have 2 cups of juice, okay? One that is labeled as pure juice and the other that is labeled as not pure, store bought, okay? Both have the same volume of juices. Let's say 50 centimeter cube, and the store bought is also 50 centimeter cube. When you taste these two juices, you will find that the pure juice has more concentration and it is more tastier, and the store bought juice is more dilute and it is less tastier than the pure juice. So this means that this pure juice have higher concentration, and due to higher concentration there are more particles in a specific volume, and this store-bought juice has low concentration and so they have low number of particles in a specific volume. So now you know what happens when you increase the concentration. Increasing the concentration increases the rate of reaction. Why? Because high concentration results in more particles being present in a specific volume. And so this increases the frequency of collision. If there are more particles present, the frequency of collision between two particles will increase. Okay? So increase in frequency of collision will result in more successful collision per unit time. If particles collide more frequently with each other, and if they collide with sufficient energy that is greater than activation energy, then the rate of reaction will increase. So now you know what happens when you increase the concentration of reactants. Now, if you were to plot this on a graph by collecting the volume, you will have a graph something like this. For higher concentration, the gradient is steeper, and for lower concentration, the gradient is less steep. So, for concentration reactions, you're going to collect the volume of the product and measure the volume of gas against time. So over here, there are two graphs shown. The gradient of these graphs shows the rate of the reaction. Okay? The faster the rate of the reaction, the steeper the gradient of the graph. So over here, the steepest graph is for the higher concentration. Okay? So the gradient is the steepest for this higher concentration, and as you can see, initially it is very steep, and as the reaction continues, the steepness decreases until it levels off. This straight part is known as leveling off. Okay? So, why is this happening? This happens because all of the reactants in the reaction are being used up, and so the reaction is complete. On the other hand, if you see the graph for low concentration, you can see that the reaction is slower initially. And this is shown by the gradient of the graph, which is less steep. And it levels off at a smaller value. Let's say this is 5 and this is 10. It is leveling off at a smaller value. Why is that? Because the number of particles available in low concentration is less, and so there will be less products being produced. So now you know how to plot the graphs for concentration reactions. For higher concentration, you will have a steeper gradient, which is shown here, okay, and which will level off at a higher value. And for lower concentration, you will have a less steep gradient, and the value will also be less because there are less number of particles. So, as there are less number of particles, less products are being produced for low concentration. Let's see some example. In your textbook, an example for measuring the rate of reaction with concentration is sodium thiosulfate with hydrochloric acid produces sodium chloride, sulfur, sulfur dioxide, and water. The rate of the reaction is measured by recording the time taken for the yellow sulfur to be formed and for the cross mark underneath this paper to be disappeared. This can be done by placing a conical flask containing the reaction mixture onto a cross on a piece of paper. First, you're going to take an A4 size paper and then you're going to mark a cross on the piece of paper. Then you're going to take your conical flask and put all of the reactants. And then you're going to measure the time for the sulfur to be produced. Okay? The time taken for this to occur will be the measure of the rate of reaction. And by that, you can see that increasing the concentration will decrease the time taken for the sulfur to be produced. If you were to plot this on a graph of concentration of sodium thiosulfate against time, in the y-axis, you can see that increase in temperature, which is in your x-axis, increase in temperature all the way from 0.01 to 0.03 decreases the time taken for the cross to disappear. If you were to plot this directly to show the difference between the rate of reaction and the increase in concentration, you can see that increase in concentration increases the rate of reaction. So, rate of reaction is directly proportional to increase in concentration. However, for this type of graph, the time taken for the cross to disappear is inversely proportional to concentration. That means increase in concentration decreases the time for the cross to disappear. And hence, the rate of reaction increases if you increase the concentration. Why is that? Because the products of the reaction that is being formed is due to the result of collision between reactant particles. In a more concentrated solution, there are more particles present, which will lead to more frequent collision between the reactant particles. And as they are colliding more frequently, they will have the chance to overcome the sufficient energy, which is activation energy, and hence there is more likely for a successful collision to take place. And overall, we know that increase in concentration will increase the rate of reaction because there are more particles per unit volume. And so, if there are more particles in a specific volume, this increases the frequency of collision. Increase in frequency of collision will result in more successful collision per unit time. And these successful collision will have energy greater than or equal to activation energy. Hence, the rate of reaction will increase. Moving on, what is the effect of pressure on the rate of reaction? Pressure is mainly for gas particles only. So the effect on rate of reaction is increase in the pressure of the reactant gases will increase the rate of reaction. How so? Because high pressure forces the particles to come closer together. Let's say you have a syringe, okay? and the particles are far apart. If you increase the pressure, this will cause the particles to come closer together. And as they are closer together, there will be more frequent collisions. And as there are more frequent collisions, there are higher chances for successful collision to take place. And these successful collision will have energy greater than or equal to activation energy. And thus, the rate of reaction will increase. If you were to plot the graph by collecting the volume of the gas against time, you're going to have a similar graph as the previous one with concentration. As you can see, high pressure has a steeper gradient and low pressure has a less steep gradient. With high pressure, the gradient levels off at a faster rate because all of the reactant particles are reacting together to give off the product. With low pressure, the particles are far away from each other and so they do not collide with each other more frequently, and therefore this shows a less steep gradient. With high pressure, you have a more steep gradient and it levels off at a faster rate. With low pressure, you have less steep gradient and it levels off slowly. Next, we are going to look at the effect of temperature on the rate of reaction. The effect on the rate of reaction with temperature is increasing the temperature increases the rate of reaction. How so? Increasing the temperature simply increases the kinetic energy, which causes the particles to move faster and collide with each other more frequently. As the particles, let's say it's a particles, it gains kinetic energy, and increase in kinetic energy causes it to move faster and to collide with other particles more frequently. And so, as they are increasing in kinetic energy, we say that particles will have energy equal to or greater than activation energy. Hence, there will be more successful collision taking place. So, the rate of reaction will increase. In your textbook, there is an example given, which is the reaction between sodium thiosulfate and hydrochloric acid. If you were to plot the graph of temperature against the time for the cross to disappear, you can see that increase in temperature from 10 to 60 decreases the time taken for the cross to disappear, which means the cross disappears at a faster rate. Increasing temperature causes the cross to disappear at a faster rate. And by this, we can say that increase in temperature increases the rate of reaction. Hence, the explanation is, as the temperature increases, the reactant particles increases their kinetic energy. Some of these particles will have energy greater than or equal to activation energy because they are moving faster. And due to this movement, there will be more frequent collisions between the particles. And this will result in successful collisions. Thus, the rate of reaction will increase. If you were to plot the graph by collecting the volume of the products and putting it in a graph against time, you can see that higher temperature has a steeper gradient and it levels off at a faster rate because all of the reactants are being used up. Steeper gradient, faster reaction. On the other hand, with low temperature, this isn't high, this should be low. With low temperature, LOW. With low temperature, you can see that this is less steep. There is a less steep gradient shown here and it levels off at a slower rate. So now you know what are the effects of increasing the temperature and how to show the difference in a graph. Next, we are going to look at the surface area of the solid reactants. The effect on the rate of reaction of the surface area of a solid reactant, let's say you have a reaction where the two reactants, one of the reactant is a solid and the other reactant is a liquid, and you're going to drop the solid into the liquid. So, increasing the surface area of the solid reactant will increase the rate of reaction. Let's say you have a huge block of solid. On the other hand, you have powdered solid. If you see and compare, you can see that this huge block, the reactant particles have less surface to collide with the solid block. But if you have powdered particles, if this solid is broken down, you can see the reactant particles will have a greater surface area to collide. More reactant particles are colliding with this solid. More reactant particles from the liquid. Let's say these balls are the reactant particles from the liquid, and this is your solid particle, the square box. So as you can see that more reactant particles from the liquid are being able to collide with the powdered solid substance. But on the other hand, if you were to put this in a liquid, you can see the less reactant particles from the liquid are being able to collide because the surface area of this particular solid is less. However, if you powder it, there are more surface area available for the liquid particles to come into contact with the solid particle. So this is why we say that increasing the surface area of the solid reactants will increase the rate of reaction. How so? If the surface area increases, more particles are exposed to the other reactant, which is your liquid. And this will lead to more frequent collisions. So there are higher chances of successful collision to take place, which will have energy greater than or equal to activation energy. And thus, the rate of reaction will increase. As you can see, a huge block of solid will allow less reactant particles of the liquid to come into contact. But if you powder it, there are more liquid particles coming into contact with the solid matter, hence increasing the rate of reaction. Increasing the surface area increases the rate of reaction. Now, if you were to plot the graph, you can see that you're having a similar graph as previous one. You're going to collect the volume of the products. For higher surface area, there is a steeper gradient which levels off at a faster rate because all the reactant particles have been used up in the reaction. But for a smaller surface area, you have a less steep gradient which levels off at a slower rate. High surface area increases the rate of reaction. Low surface area decreases the rate of reaction. And that is why there is a difference in the steep. This steep shows that the reaction is faster, and this less steep gradient shows that the reaction is slower. One example from your textbook is the reaction between hydrochloric acid and calcium carbonate. This releases calcium chloride, carbon dioxide, and water. We know calcium carbonate is a solid substance. And if you powder the solid substance, also known as limestone, you can see that both of these reactions will occur in a neutralization reaction to produce carbon dioxide and a salt. As you can see, these two reactions are showing the difference between a chain with higher surface area and lower surface area. With lower surface area, you have less fizzing, as you can see here. With low surface area, which means block of metals, you have less fizzing, which means that this reaction is slower. However, with powdered metal limestone, not metal, with powdered limestone, you can see that there are more fizzing showing, which means the rate of reaction has increased. And you can find the rate of reaction of these two reactions by measuring the volume of carbon dioxide produced and the loss in the mass of the reaction mixture with time. And these two methods are generally used for measuring the rate of reaction process involving the formation of a gas as one of the products. So, how do you measure? You measure the mass using a balance, and you measure the volume of the gas being produced using a syringe. And that is how you find out whether surface area affects the rate of reaction. As you can see, blocks of metals or blocks of solid reactants decreases the surface area. But if you cut it up, slowly the surface area increases. Eventually, if you powder it, the surface area increases to the highest point. And if you were to plot the graph of temperature or time against loss in mass of the reactant particles, you can see that with powder limestone, you have a steeper gradient, which shows that the loss in mass is very frequent. But with lumps of limestone, which is blocks of limestone, you can see that the loss in mass is slower. It's not steeper, it's slower as time increases. Hence, if the surface area of a reactant is increased, there are more particles being exposed to the other reactant. So the rate of the reaction will increase.